Okay, let's continue the discussion of tutorial 3 for problem 3. Okay, for problem 3. Problem 3, what we have is that we have to do the closed integrals, closed circular path integral and then closed rectangular path integral for the given vector fields. So first we will do the anti-clockwise circular path centered at the origin with radius r integral. And for f2, then we will go for a clockwise rectangular path centered at origin with length 2a along x direction and breadth 2b along y direction for f2. Okay, we will see what are the results coming there, and there will be some physics behind it to discuss after that, following that. So first of all, let's do the first part, that is along circular path. Anti-clockwise direction, anti-clockwise. Okay, so let me draw the figure, and we are doing for f2. F2 was equal to b2 into y square x cap minus x square y cap. This was your v2 force and the figure. So this is your f. Now the coordinate system here, then this is the radius, and let me denote the radius capital R because it's fixed, and this is the theta you have, right? So since we are doing in the circular path, the coordinate system we can use, the best coordinate system to use is the polar coordinate system. Okay, by polar coordinate system, then the problem will simplify. Okay, so how will you take into the polar coordinate system? We know from our previous discussions and all, the relation between x cap and y and r cap and theta cap, we know that is equal to cos theta r cap minus sin theta theta cap, and for y cap it is sin theta r cap minus plus cos theta theta cap. This is for x cap and y cap, and x is related as r cos theta. This is capital R because so it is a circle and it's centered at the origin, and y is equal to r sin theta. So we substitute in the f2 what we will get for f2. What is f2 is, so therefore f2 is equal to b2 into, so y, now therefore we have to write y square, that is r square sin square theta. Okay, that is y square into x cap. Now you have to write as cos theta r cap minus sin theta theta cap minus, now what is your x square? X square is r cos theta, so that will be r square cos square theta into, again for y cap, that is y cap here, that is sin theta r cap plus cos theta theta cap. This is your form of the function f2 now. Right, now look at what is dl. So what you have to find is the path integral. So that is along a path closed loop f dot dl. That is you have to find out. Okay, it's the path integral means along a line you have to follow. So the dl, you have to find out dl here on this one. So what will be the dl here? So let's say this is the path I am following. So this is the dl for me. So what will be the dl here? To find out dl, you just find out what is the angle changing. So there is a small angle d theta changing. Therefore dl I can write as r d theta into theta cap. Okay, so what will be f2 dot dl? F2 dot dl now therefore equal to, f2 dot dl is now therefore equal to f2 dot r d theta theta cap. Okay, so which is equal to f2 dot theta cap into r d theta. So what is this f2 dot theta cap? Which means only this theta cap part will be remaining, rest of this r cap part will go. Okay, so just dot product it and find it out what will be equal to. So that will be equal to r square into sine cube, r square into sine cube, which is coming from here and it is negative, minus r square into sine cube minus r square into cos cube. That will be like that. Okay, so minus of sine cube theta plus cos cube theta into r d theta. This is what you will get. Fine, I hope this is clear for everyone. So now we got what is the form of f2 d theta. Okay, so and there is a b2 also, there is a b2 also which is missing here, so which I am adding here. So finally this will be equal to minus of b2 r cube. So there is a r square term from f2 coming and a r term from r theta coming, so therefore r cube into sine cube theta plus cos cube theta d theta. This is your f2 dl. So now let's do it for the whole closed loop. So what it will be equal to? So f2 dl is equal to minus of b2 and r cube. I am taking out of the integral because they are constant. So into sine cube theta d theta plus closed integral of cos cube theta into d theta. So this integral goes from 0 to 2 pi, right? Closed integral matlab this is going from 0 to 2 pi, and you see this one is equal to 0. So there is an alert I am putting here. You remember the same force when we calculated earlier gave us del cross F equal to 0, but now not equal to 0. Now I am getting this F dot dl equal to 0. I said in the previous discussion that this del cross F not equal to 0 is a non-conservative force, and for a conservative force this path integral will give you equal to 0. What is happening? There is this I have this part we will discuss towards the end of this problem, just after the rectangular path. Okay, because for the rectangular path also you will get the answer equal to 0. Now why is it equal to 0 and why is it not equal to 0 will be coming there. So now let's look at the rectangular path. So for rectangular path, let me draw the figure first. Okay, so let me draw the Cartesian coordinates to it. And okay, Cartesian coordinate here. Let me denote the coordinates. So we have given that it is going from 2a along x-axis, so which means minus a to b here, and 2b along y-axis. Okay, these are the coordinates. Okay, now we have to follow this this path, clockwise path here. This should be the path of the integration. Now I will consider dl here. This is the direction of dl. Okay, so now f2 dl for each line we have this. We have to find out the work along this closed path f dot dl, f2 dot dl, that is the force. So now I can just split this force along this different paths. I am denoting this path as 1, this as second, this as third, this as fourth. So now I can write therefore this one equal to integral along f2 first path, okay, into f2 dot dl plus integral along second part into f2 dot dl plus integral along third part into f2 dot dl plus integral along fourth part into f2 dot dl. Okay, this is how that integration is. Now let's do for each part. So let's do for the first part, this one. Okay, integral along f2 dot dl. You will see this is equal to, here when you in this path you see this y is not changing. Okay, the dy part is equal to 0. So before I write this one, I can write this as f2 dot dx x cap plus dy y cap, that is your dl. Okay, so along this path dy is equal to 0 here, dy equal to 0, and y is simply equal to b. Okay, because this path y is not changing. If you look at the figure, the y is not changing, so dy equal to 0. So I can write this equation now equal to, and since only yeah, that I can write here and we can discuss after that, f2 dot dx into x cap. This is what you have because dy part is 0. So now only the x component of f2 will be contributing, so that is simply equal to 1 into y square into dx. Okay, now what is y square here? Y square is y is equal to b there, so that is simply equal to b square into dx, integral of dx. What is it, b square? This dx is taking values from minus a to a, right? Minus a to a, so that will give you integration from minus a to a. So this will give you values equal to 2, and there is a B2 here when you are applying the force. So this is equal to B2 into A B square. This is the answer for the first part. Integral of F2 dot dl. Okay. In the similar way, I am going to do for the third part. Okay, and F2 also you can do. In F2's case, you see that here dx part is constant. Okay, so in the similar way you can do for the second part. Now let's look at the third part, what I am getting. In the third part, if I get again you see here in the third part dy is equal to 0 because y is equal to minus p. Yeah, okay, so for third part I am writing it for third part F2 dot dl. If I take it, this is equal to y square x cap minus x square y cap into dx x cap minus dy y cap. Okay, you see y is this part again 0, right? And this therefore only the x component part will be remaining, so that is into b2. So that is b2 into, and y is equal to b and dy equal to 0. That's the reason why this part is vanishing. So now b2 will become b square. From now, look at here, only the x component part is remaining, so this is simply integral of dx, right? From where to where now? A to minus a. So what will be the answer for this one? This will be minus 2b2 a b square. Now look at this one. First one, that is for the first part, when we integrated it, we get this one here, and for the third part we got integrated, we got just opposite value, negative value. So this both will, when you add, substitute it here, this both terms will vanish, this term and this term will vanish. In a similar manner, you will see the second term and the fourth term also will vanish. In the second term and fourth term, what you have to do is like I said, this x is simply equal to a and it's not changing. So dx is equal to 0 there. So the values you will get will be for the one part, it will become one of the part, it will become, answer will become like equal to 2b2 into a square b, and the other part it will become 2b2 into a square b. So that part, this both will get cancelled there also in a similar manner. And at finally what we get, this work done along this closed two path, again F2 dot dl is equal to 0. Exclamations again. What is happening? Like I said earlier, del cross F2 was not equal to 0, and we commented this one as a non-conservative force, and even after when we are looking this F2 dl, we are getting it equal to 0. For conservative forces, it has to vanish. What is happening here? So this point is that this is not true if for this may not be true for all the paths. Only we took only one or two paths here, circular path and a rectangular path. Let's take a semicircular path. What will happen? Let's see. In a semicircular path, what will happen? Let me draw a semicircle and erase the non-semicircular part. I will erase now. It's okay. And erase the one part of it. So I get the semicircular path here. Okay. And let me draw the coordinates for it. And these are your coordinates. Okay, right. So and integrate it along this path the same way we did for the earlier discussion. So I'm going it in this path, the dl is here. Okay, and from here I am going this path. Okay, so let this be minus a and this is a, or capital minus r and r, whatever you call it, because we took it r. So now let's do this integral. So what we had was the integral equal to f2 dot dl. f2 dot dl was equal to f2 dot theta cap into rt theta. This is what we had. And when you are taking this closed integral, now what we can do is that this first you can integrate along the circular path 0 to pi. Okay, f2 dot theta cap. And now you can do this integral along the straight path also, rd theta. Okay, and that straight path I am doing in the Cartesian coordinate system, which is also possible. You can do split the integration between polar and Cartesian coordinate system. So this is becoming from r minus r to r, f2 dot dx x cap plus dy y cap. This is simply you apply both cases there. So what was this f2 theta cap? If you remember, we had calculated f2 theta cap here. Let me take that value from here directly. So now f2 theta cap was equal to this one, this term, sin cube theta d theta plus cos cube theta d theta. So this is equal to 0 to pi sin cube theta d theta plus 0 to pi, and there is a global b2 into r cube, that part is there, which we should not forget, sin cube theta d theta into cos cube theta d theta, this part is also there, plus now along here we have this f2 term dx and dy. Now here only the x term is changing, the dy part will go, so the only the x component of f2 we have to worry about, so that is b2 into integral of, and what is the y value there? Y value is we will take that value soon, y square into dx from where, minus r to r, this is what it will become. So what is the y value here? Y value here is 0, so therefore this term will vanish to 0 because y equal to 0, okay, because of this reason. Now what about this one? If you do this integral, you can do this by substituting this as the sin cube theta. Now you can substitute this one as sin theta into sin square theta, and do it like sin theta into 1 minus cos square theta. Now substitute for cos square theta is equal to x, and then differentiate it. You will find out what is dx is equal to, like that, and use the substitution method and find out the answer. That part you do. You will get answer should be equal to something like 4 by 3. Even though this is a closed integral, we are getting this is not equal to 0. The thing is, like, I will summarize what I did now. Summarize what we did. So when we use circular path along along clockwise direction, with origin at center, we got this f dot dl equal to 0. Similarly for rectangular path. Okay. Now third point, we had obtained del cross f not equal to 0, therefore this f force was not a, therefore f2 was not equal to 0, and f2 implies non-conservative. This was our dilemma. And to check it, what we did is we took a next is, and we checked for another closed loop along a semicircular path, and what we obtained is that this f2 dot dl not equal to 0, which means this f2 is not a non-conservative force. For a conservative force, this closed integral with any loop f2 dot dl is equal to 0, because that I will explain you from the Stokes law, which I said, that is del cross f dot dA is equal to f dot dl. Okay, this term, once it is equal to 0, means this term has to be 0 everywhere, right? With that should not be like this one path it is 0, the other path is not 0. It will not happen for a conservative force. Okay, through every possible path, the conservative force has to be equal to 0. Not like along one path it's 0, along some path, other path it's not equal to 0. That's not possible for a conservative force. But for a non-conservative force, conservative forces, what can happen is that in some parts, depending upon the symmetry of the function and symmetry of the path and all, you know, some path this integration can vanish. For example, what happened here? Here there is this one, this is about the rectangle, and both the circle and the rectangle both has a symmetry. Okay, for it was a symmetrical path, and along that path this force also had some kind of symmetry along it, with, and when you took this integration it vanished. But when you did that for the semicircular path, that symmetry did not happen. Even though semicircular path has a symmetry along along this y-axis, it doesn't have any symmetrical change along the x-axis. This function required that to vanish. This field required that to vanish, which is not happening. That's why semicircular path you did not get it equal to 0. So basically this F2 is a non-conservative force. Only because of that path, that particular path, we got it as equal to 0. So the point is that this a conservative force, for a conservative force all the path integral will vanish, but for non-conservative forces some closed path integral may vanish. That doesn't mean that function is a conservative force. So the only method to check if force is conservative or not is to take the curl of that function. Okay, so watch the video again, convince yourself. If you have any doubt now, comment me in the comments, let me know in the comment section or in the Teams group. Okay, so thank you for watching this problem 1, 2 and 3, and have a nice day. Question number 3 and 4 also will be discussed, and thank you for watching again.